Part D, we're asked to show that P satisfies the logistic equation dp dt equals P times 50 minus P over 10. Okay, so to show that this satisfies this differential equation, we have to plug it in and show that it checks. So the first thing we need to do is to find dp dt. So I need to take the derivative of this with respect to t. Now, what I could do, or I should say what I should do, well, I could do the quotient rule on this, which is a bit of a waste because the numerator here is a constant. So what I'm going to do is I'm just going to rewrite P of t as 50 times 1 plus 4e to the negative 5t to the negative 1 power. And then when I take the derivative of it, I can just use the generalized power rule. So the derivative of this would be, the negative 1 would come down, would be negative 50 times 1 plus 4e to the negative 5t times the derivative with respect to t, to the negative 2 power. So that's the power rule, negative 1, that thing to the negative 2, times the derivative of what's inside. So this is negative 50 times 1 plus 4e to the negative 5t to the negative 2nd power times the derivative of what's in here. So that derivative is 0. The derivative of e to the negative 5t is negative 5e to the negative 5t, but I've got the 4 out there, so I'll put that, multiply that to give a negative 20 e to the negative 5t. And when I go ahead and clean this up, I've got negative 50 times negative 20, which is a positive 1,000, e to the negative 5t over that. So that's dp dt. What my job is to now look at this side of the equation and show that when I simplify this side of the equation, I also get that. All right, so that's my next challenge. All right, so let's start P times 50 minus P over 10. And I want to substitute this into that. So I'm going to have the 10th, I'm going to leave that sort of as a fraction out front and just have P times 50 minus P and now I got to simplify that. So I'm going to have 1/10. Well, let's see, the 1/10, I can go ahead and cancel that out and get a 5. So now I've got a 5 over this guy. And to subtract these two things, I need a common denominator. So if I think of that as 50 over 1, multiply the numerator and denominator by that. So I have 5 divided by 1 plus 4e to the negative 5t. So let's see what happens. Now I have the same denominator. Let's see what happens in the numerator. Well, when I multiply this through, look what happens. I get a 50 times 1, so I get a 50, plus I get a 50 times 4, which is 200, e to the negative 5t, minus 50. All right, so my denominator, I've got this times that, so I get that quantity squared. And what's going on in the numerator? I've got 50 minus 50, so they cancel out. I got 200 times 5. So what do I get? Lo and behold, 1,000 e to the negative 5t, which is exactly what we got when we simplified the derivative. All right, so that shows that P satisfies that differential equation. That'll do it for part D. All right, part E, we're asked to use the differential equation to show these two facts about the population function p. So for part 1, we're asked to show that p is always increasing. So from Calc 1, we know that if p prime of t is always bigger than 0, then we can conclude that p is increasing. So if I look at this differential equation, p prime of t, which is just another way to write dp dt, is equal to this. Now, if we go back and look at the original formula for p of t, we note that for any value t, e to the negative 5t is a positive number, and hence 4 times e to the negative 5t is also a positive number. So that means that p of t is equal to 50 over something bigger than 1. Which means that p of t is always between 50 and 0. So with that observation, note that p prime of t, which is equal to this, that's always bigger than 0 because p is bigger than 0, and that's always bigger than 0 because p is less than 50. That means this is always bigger than 0, hence p is increasing. All right, so just using the differential equation and a little bit of number sense, we can prove p is increasing without resorting to taking the derivative and making a sign diagram. So that'll do it for part 1.